My name is Mantao Huang. I'm in Professor Jeffrey Beach's group working on solid-state color pixel for electronic paper displays. We perceive the world by seeing, so we always want better display technologies. Most of us look at displays multiple times every day, but it was not until the early 20th century that we invented the first black and white cathode ray tube CRT display. And with several other technological leaps, we invented color CRTs and flat panel displays. You probably have one of those right in your pocket on your smartphone. But we are not satisfied with these displays because they work by shooting light towards us instead of using any of the ambient light that's available. So they consume unnecessary power, and they look faded under strong ambient light conditions. And more importantly, this is not the natural way we evolved to perceive the world. So we see our surroundings by reflection of the ambient light. To overcome these problems, we invented electronic paper displays, such as those used in Kindles. And unlike normal tablets, Kindles have good readability even under strong ambient light conditions. And this kind of display are usually easy on eyes and have low power consumption. And this amazing technology enabled a fast-growing market. But why we don't see electronic paper display replacing all the flat panel displays that we see everywhere? That's because the current technology still has some limitations. So these displays have slow response rate and have limited pixel density and limited color capability. And why is that? Let's take a look at the current technology. So on your right shows an electronic paper display, and that consists of millions of capsules like that, and each capsule consists of many microparticles with different colors and opposing charge. And by applying a voltage, you can drive these microparticles up and down like this or that. But the problem here is that the capsule is on the order of 100 micron in size, so that these microparticles need to travel a long distance to go to the other side to change the color. So these displays usually have slow response time. And also because of the size of these capsules, these displays have limited pixel density. So what can we do about this? We ask ourselves. So in our group, we work with ultra-thin solid-state films. And recently, we discovered a thin film where we can apply a voltage to drive the atomic-sized ions inside this material to change its color. And the difference here is that the ions that we are driving are much, much smaller than the microparticles used in the current technology, so that we can make our device very, very thin. So this figure shows the thickness comparison to the current technology. Because of this, we can achieve very high pixel density. And because these ions don't need to travel far to go to the other side, we can achieve fast response time. And also, due to the ultra-thin nature of these devices, they are compatible with flexible substrates. So here, let's show a demonstration of a blinking pixel. So with very simple material and structure, by just applying a small voltage, you can change its color reversibly. And the color goes one way or the other depending on the polarity of the voltage you apply. And there's no backlight, so it uses just the ambient light. And the good thing here is that when the power is off, the color remains unchanged, like that. So this figure shows that it's very straightforward to fabricate pixels just like that one, but with a variety of different colors to begin with. And by applying a voltage, they can be changed to the corresponding color as shown in the bottom row. And yeah, by just reversing the voltage, we can get the original colors back. And here we show that we even achieve the capability to display multiple colors from just a single pixel. So this one, for example, it goes between yellow, red, and blue just by applying a voltage. What's more exciting is that we can use this kind of mechanism to control the color at ultra-high resolution. So here shows an example of a dynamic color image of a leaf. So by applying voltage to different parts of the image, we can change the colors of the corresponding regions. And the amazing thing here is that the size of the image is very small. It is even smaller than a single pixel of a smartphone, which is comparable to the typical size of a human hair, as shown here for comparison. So this ultra-high resolution capability means that our technology could be suitable for virtual reality display and holographic displays. So what are the potential applications of this technology? Here are some examples. Wearables, electronic readers, electronic science, virtual reality displays, or holographic displays. And with our technology, we hope to make this happen. We thank CMIC and Deshpande Center for funding support, and we thank our catalysts. I thank my advisor and my group mates for support. And if you are interested, please come to our poster session to learn more. And thank you for your attention.